In this video, I'm going to go through an example of evaluating an integral using u substitution that's a little bit trickier. It's kind of hard to see exactly how this is going to work right off the bat. So here's our integral where I have the square root of 1 plus x squared times x to the 5th dx. Now when you're using u sub, what you're looking for here is a composite function, and you want the inner function of your composite function to be what you let u equals. Alright, so here I have a composite function. Ignoring this x to the 5th, this is a composite function where the inner function is 1 plus x squared and the outer function is square root x. So usually I'd say, alright, I'm going to let u equal this inner part. So I'm going to let, let's go all the way over here. No, we'll do it here. I'm going to let u equal 1 plus x squared. Great. Alright, then you have to substitute in for this dx. Well, this x to the 5th is worrying me here. I'm not exactly sure how I'm going to get rid of that, because my du dx, if I take the derivative of both sides of this with respect to x, I get this. So I know that du equals 2x dx. So, okay, well, let's see. I could rewrite this integral as 1 plus x squared times x to the 4th times x dx. Okay, and I need, for my du, I need a 2x dx, so I'm going to put a 2 in there and a 1/2 there to balance that out, right? If I multiply by 2, I got to times by a half. So, okay, well, this is looking pretty good right here. This is going to be my du, right? That's going to be my du. That's great. This business right here is going to be my u. I've got that here. But now I've got this x to the 4th hanging around. All right, so this is a little tricky one here of how we can deal with this x to the 4th and still use u substitution to write this integral all in terms of u. All right, and the way we're going to do that is with this guy right here. We're going to solve this for x squared. All right, so if u equals 1 plus x squared, we know that x squared would equal u minus 1. All right, so here I have an x to the 4th, which is x squared times x squared, right? X squared times x squared. So I'm going to substitute in u minus 1 times u minus 1. I could also just keep going here and say, alright, I'm going to square both sides of this to get my x to the 4th. Let's use a different color. Or you could just put in 2 factors of u minus 1, or we could do the work beforehand. Let's say I square this because I need an x to the 4th, right? So I have x to the 4th is equal to u minus 1 times u minus 1, right? Which is what I'm going to do here, x squared times x squared. Alright, let's write this all out in terms of u and see what we have here. So I've got the half. Alright, I've got my integral. I haven't integrated anything yet. I'm just doing a u sub. So this turns into a u, square root of u. This x squared is going to be a u minus 1. This x squared is going to be a u minus 1. And then all this business here, this 2x dx, that's going to be du. Okay, is this an easier thing to integrate? Like this guy, my original problem, I couldn't integrate that. I got a product, I can't, it's nothing to do here. So have I made an integral in terms of u that I actually can integrate? Well, the answer is yes. All right, and the way that we're going to do that is we're going to multiply all this stuff out. We're going to change this to u to the half. Let's go ahead and FOIL this business out. So we have u squared minus 2u plus 1. And then I can distribute this u to the half in there. So I'd get 1/2 plus 2 is 2.5, right? Which I'm going to write as 5/2. Remember, we add the exponents there. Minus 2, and this is u to the 1, so 1 plus a half is 1.5, or 3/2. And then we have u to the half. So now I have this all written out just as powers, and I can do the antiderivative of those using my antiderivative power rule, which I'll write over here just in case we need a quick review of that. Alright, so let's write that. The integral of u to the n du would be 1 over n plus 1, u to the n plus 1 plus a constant. So that's what we're going to do over here. Yeah, we got a lot of fractions. We're going to have to deal with these fractions. It'll be alright. Okay, so I'm going to write that over here. So I have 1/2 times, I'm going to do my antiderivative. So let's see, 5/2 plus 1 would be 7/2. Let's see, how much of this do I want? I'll write it all out. Whenever I question how much should I write out, the answer is just write it all. So I have 1 over 7/2 u to the 7/2 minus 2 over 3/2 plus 1 would be 5/2 u to the 5/2 plus 1/2 plus 1 would be 3/2, so 1 over 3/2 u to the 3/2 and plus a constant. Okay, so this is, let's make sure this is out of the way here. This is alright, so now we just need to clean this up a little bit with our fractions. So when we're dividing by a fraction, that's the same as multiplying by the reciprocal. So this is 2/7 u to the 7/2 minus 2 times 2/5 u to the 5/2 plus 2/3 u to the 3/2 plus a constant. And it doesn't matter whether the constant's inside or outside these parentheses because it's a constant. If you multiply it, well, in this case, right, it doesn't matter. We don't have any initial conditions or anything like that. So all I have to do now is distribute the halves. So that's going to give me 1/7 u to the 7/2 minus, let's see, that's 4/5 times a half. It's going to be 2/5 u to the 5/2 plus 1/3 u to the 3/2 plus a constant. Now if this was a definite integral with a lower bound and an upper bound, then we could have made that substitution with this u equals 1 plus x squared and put some different bounds and just went ahead and evaluated that with the u's. But since this is an indefinite integral, we do need to write our answer in terms of x. So we're just going to substitute 1 plus x squared back in for u. So 1 plus x squared to the 7/2 minus 2/5 1 plus x squared to the 5/2. We're almost done here. And there's really not too much you could do to clean this up. If you're tempted to, say, multiply this 7/2 into these parentheses, don't do that. You can't do that, right? This is with a plus here. You can't do that. If this was multiplication, we could do that. I guess the only thing you could maybe do is factor out a 1 plus x squared to the 3/2. I'll just do it for fun. I would accept this answer myself, but maybe your instructor would want you to do this. Remember, when you're factoring out a greatest common factor, you factor out the smallest exponent, so in this case it's 3/2. It does kind of make it come out nice. You'd get 1/7, and then you'd have 1 plus x squared. Now this can be a little tricky for some people. To figure out what this exponent is, you have to figure out 3/2, that's 1.5, plus what would give you 3.5, and that answer would be 2, right? So 1.5, remember you add these exponents if you were to distribute this. So 1.5 plus 2 is 3.5. Minus 2/5 times 1 plus x squared. So here's 1.5 plus what gives you 2.5. That's just 1. And then that whole thing got factored out. So, you know, writing it that way, I get I get rid of some of my fractional exponents. I guess that's a little cleaner, but either way would work. Alright, so I hope seeing this example of using u-sub to evaluate an integral that doesn't really look like maybe it's a good candidate for u-sub at the beginning, I hope it was helpful. The key is just try it, you know, see. If this would have been u to the third, or x to the third right here, it wouldn't have worked very well. Oh, maybe I hate to say that without trying it. It would have been a little bit tougher. But again, that's the key. If this was a x to the third, you know, maybe give it a try and see if you can make it work.